And yes, I think I will hand off to Dr. Su now to begin his presentation.
Cool. Thanks, Harris, for your great introduction. And I will share my screen. Cool. Can everyone see my screen?
Yes, we can see.
Cool. So today, my talk is about the beta lesson of AI. So it's actually from an essay written by Professor Rich Sutton, one of the fundamental founders of reinforcement learning and the author of the Introduction of Reinforcement Learning book. And I will expand from his essay and then elaborate a few key points I found like very inspiring for like our like younger generation of researchers. First of all, like a bit of a brief introduction about the C Limited company. So we are a leading global consumer internet company founded like in 2009, and C Group is the umbrella group company. We have like sub companies as Garena, which is a very famous gaming company, and Shopee. I believe like many of you have used that for shopping. And we also have like a digital finance company, C-Money. And our mission is to like serve better the lives of the consumers and small business. And CAI Lab is a newly founded, the lab was founded less than half year ago, and we have been making the mission of like pushing the edge of the AI with technology. So the essay I mentioned, like you can find by the link here, which is written by Professor Rich Sutton, and it's a very beautiful essay. And I think the idea conveyed there is super clear, and I would like to like advocate his great point of the beta lesson of AI. So the essay is written from his like decades of experience of AI research, and I think it's a much bigger vision and longer term view than like the recent deep learning breakthrough, and it covers like classic AI as well. So it's really like a great essay. That's why I would like to echo the points here. So one of the key points in the essay is that we should have less inductive bias into our model and our ideas so that the idea could be more general. So what was called the beta lesson is that people like, especially like researchers, we tend to focus on certain improvements and in a way that by putting human knowledge into the AI algorithms. So such as that if you would like to build a chess program, you would utilize many like building rules and human heuristic, human knowledge and putting all of them into a rule-based chess program. And in the short term, like given the situation, like decades ago, the compute power is not enough. That brought people like a lot of improvements. So it's like, it's also benefit from the researcher's point of view because not everyone would like to like wait for decades for a breakthrough to happen. So everyone need to make progress at some point. So people tend to focus on short-term impact. And in the long term, as we have witnessed in the past decades, breakthroughs often happen when removing all of the inductive biases. and making the algorithms more general. We can see like many examples in the following slides. So the second key point Professor Rich Sutton made in the essay is that we should leverage the compute power as much as possible. So based on the model, so your compute power can be like multiplied every year or every a few years, and then it remain also true because apart from the CPU improvement, we have now more advanced compute devices such as GPU and TPUs. So in order to leverage all of the improvement from the hardware, in the point of algorithms, we should only use the algorithms which can scale up with the compute as much as you want. So there are two families of algorithms which can fit this requirement. First one is search. So you can view it as like you could parallel a lot of like enumeration, and so that you can find out your optimal solution. And the second one is about learning. So it's like leverage the gradient descent, mini batch, and then you can learn the model. So these are the two ways, like you give it as much as compute resources, it can scale up. So in the history, the first example of the breakthrough of like making algorithms more general and then it can make it more powerful is Deep Blue. So before Deep Blue, the chess program was written like really in a really handcraft way. And Deep Blue make the breakthrough by a few ways. They even build like customized hardware for the program. They use like alpha beta search for the chess, so that like I think it was decades ago, but they managed to leverage the power of search. At that time, they built special machine for that, and that as people all know nowadays, that it beaten the world champion at that time. Another great example is Alphago. So it happened a few years ago, and I think it's fair to say that the this event brought the biggest impact of the artificial intelligence to like very general public. So due to this event, people, including researchers and industry people, and also general public, they are aware there's the great power of AI. And for AlphaGo, so the difference between AlphaGo and the previous Go program is that AlphaGo leveraged like the two important things we mentioned just before. So the first one is about search. The other one is about learning. So here, like the first generation of AlphaGo, they learn from the human expert Go play records. So you can see that they can learn from the human expert positions and then train deep neural network to mimic the human experts. And then later they use the powerful self-play algorithms to continuously improve the AI. And the self-play idea is really simple and clear. So it's just like you train an agent, but for the opponent, you just use the agents from the previous iteration so that you can always beat your previous trained model so that you can always get the improvement. So the series of AlphaGo program is also itself a demonstration of reducing inductive biases and getting more general. So in the second generation AlphaGo program, which is called Alphago Zero, there are a few key changes here. Arguably the most important one is that they no longer use the human position data. So completely removing the necessity of training from human data. And as you can see from the GIF here, the Alphago Zero program can fully train from scratch, and then it can learn to beat like world champion, and then also learn to beat the previous strongest version of Alphago. So why is this important? Like, why is like pure self-play without human player data is important? Because it's removing the necessity of collecting data, because it is a really human like a human labored effort which cannot be automated. So you have to get the top players to play the game, and then you collect the data so that you can train the program, which is not general enough, and it's introducing a lot of like human inductive biases. So by leveraging the self-play algorithms, the program can fully master the game by itself, by just learning from itself and self-play. So that's like very beautiful, and also is super general. And the second improvement includes that the features are now fully learned as well. So it's not in the first generation of AlphaGo, there are like quite a lot of input features that are handcrafted, uh, like according to the Go expert human heuristic. And in this second version, it is only like fully learned from the ball position, and the learning and the parameterization of the network is by a deep ResNet. So to the third generation of AlphaGo, which is the Alpha Zero, we can see like immediately see the benefit of like removing the human data part. Because like for Go games, you may have a data set so that you can immediately train from this data set. So when you switch to another game, you may need to find another like large scale data set so that it can allow your supervised training from the human data. And by introducing like purely self-play, as demonstrated in the Alpha Zero, without significant change of the algorithms, you can train a very powerful agent. So it's almost the same algorithms, but with different neural network architecture. They can play chess, shogi, and Go. So as we can see, there are different games, but with the same general algorithms, you can as you can see in the statistics, there are really strong players on each of the game. And the most up-to-date version of Mu Zero even pushed this further. And this beautiful like illustration also summarize the fourth generation improvement and what kind of domain knowledge they apply. And you can immediately sense from the illustration that step by step, like from the first generation, and then to the current one, it is like step by step removing the human knowledge. Like at the very first generation, it has human data as the input to train the supervised policy. It need like domain knowledge to design the input features of the network, and it know all of the rules about the game of Go. And then finally, as you can see from the Mu Zero, all of the knowledge are removed, and it is the most general version of that, because as you can see, the domains grew from only playing Go to playing both Go, playing like all of the games listed here, including video games, Atari. So this is a great demonstration of like a research uh, philosophy, which is that by removing prior knowledge, by removing the inductive biases, the algorithms become more and more general. So there's not only like examples from DeepMind can demonstrate the idea of scaling up and then removing biases. There are also like many other demonstrations as well. For example, OpenAI 5, which is the uh, the uh, Dota 2 top AI program, which can beat the professional and champion team. So the core algorithm is really, really simple. It's just scale up the well-known reinforcement learning algorithms, PPO, with the compute of like 1,000 GPUs and like 50,000 CPUs. So that's like, I think that's the key idea. It's like not is leveraging the compute power and also is identifying a really strong algorithms which can allow you to scale with the compute power. And yeah, this is a really just a simple illustration of the algorithms. So just you put a lot of CPUs for simulating the game, and then you put GPUs for both learning and acting of the game. Another example is like is very classic for the computer vision application. It is for CommonNet. So in the previous decade, so before 2012, all of the people in the computer vision community is using handcraft features like Shift. So you need to be aware of the histogram like distribution and then to make your feature as the input to your classifier. And then later with the breakthrough of AlexNet, this input feature can be fully learned. So that's like really removing the prior knowledge and the expert domain data. So it actually do not require you to understand anything about computer vision. You just put your image, fixed size images as input, and then it can give you the classification output. And I think after almost 10 years, people have witnessed like all of the breakthroughs from this change. So this really allows various of applications and really ease researchers' life from like applying the same techniques in like every single place. Another recent example is transformers. So it was just proposed a few years ago, but it has a really huge impact. So why is this? So it's what's like different between the transformer and the previous models of like natural language processing or computer vision. So one key factor is that it's, as you can see from the transformer architecture, it has many building blocks, but one of the key building block is just like matrix multiplication. So you have the Q matrix and then key matrix and value matrix. They all like they all can be composed together by simply matrix multiplication, and we can and as we all know, the matrix multiplication is the most effective way, like people have been optimized it for decades, either from CPU or like NVIDIA GPUs or TPUs. Like I think numerous engineers have been working to improving the speed of this. So, so having this kind of structure and having the matrix multiplication as the major component of the transformer allows transformer can scale up with arbitrary compute, which is the key point Rich Sutton made in his essay. So what this has told us is that people really should focus on some general ideas which could work like decades and can be applied in many, many different scenarios. So even it wasn't the domain it was proposed, but if it is general enough, it can be applied everywhere. Like ResNet, it was proposed in image classification, but in the end, it was applied in the Alphago Zero network, and now it's like everywhere. So these kind of general ideas, they are very few. I am listing like just a few examples here, but actually like it's really hard to find these kind of big ideas. So they include like ideas which allow like backpropagation and SGD. You can train your giant data and your giant model from just really simple scalable algorithms, these kind of optimizers. And other examples include the neural networks. So all of these neural networks, they are really universal and can be applicable in all of the AI applications. And specifically for the reinforcement learning algorithms, these are decades old algorithms, but they are still applicable in all of the largest complex video games agents up to date. So they are like, I think the mission of the researchers and for the younger generation of students, our mission is really to innovate on the general ideas so that we can target on the biggest impact. Another fact, like apart from the algorithm improvements, we have witnessed like giant hardware improvements in the past decade as well. So as you can see, like the GPUs and the TPUs are the most biggest improvement as we can see. And one key point I would like to make here is that nowadays, with the modern computer architecture, we can say the idea of single machine has been redefined. So here we are listing actually in certain concept it is from a single machine because it is from a TPU port. It consists of 4,000 more like TPU cores, and as you can see from these like amazing numbers, like it takes less than half a minute to convert on like a ResNet model. So this kind of compute power is like really amazing and really unblock lots of big applications. And to some of the the powerful single machine you can purchase or your research lab can purchase, they are also very powerful. For example, the NVIDIA DGX workstation, like just a single machine, you can place it on your lab or in the data center. They can provide 5 petaflops. Like that's like a lot for the AI tasks. So, and it's really single machine, so it do not require researchers to understand anything about distributed computing. But at the same time, you can achieve a lot by leveraging the full compute power. And here is another illustration of the power of single machine. So here, I think like Google did a great job of the great visualization is to highlight like how much compute power can it bring? So one TPU port. So the one TPU port, it can be bring your power larger than 10 million laptops. And like here, like each icon represent 100,000 laptops compute power. So here is like really just an obvious illustration of that this single machine. And at the same time, I think the programming model for that is really a single machine. So you do not really need to think about the heavy drop on the parallelization. By building this kind of giant machine can help researchers focusing on their key ideas instead of infrastructure. And to conclude a bit on the previous points, I think I think my personal view and many, I think it's also shared in many of the researchers that it is nowadays there are like great opportunities for the generation. So there are like a few key components for the AI research and AI applications that they are all in a very good stage. For data, we can have many great large-scale data set we can train our models on. And for compute, as we also just mentioned, there are like a lot of supercomputer and the programming model are simple. We can leverage those giant compute power on our application and research. And there are like numerous ideas flowing around every day, numerous research papers published each year. And I think really we should just take this golden age and then to like show our like abilities. Yeah, I think at the end, really just a brief introduction of our lab. We are digging deep in AI fundamental research, and we are like having a long-term view and vision. The lab is directed by Professor Yan. And if you are interested in our lab, you can drop me an email and check out our website. Yeah, I think that's all of my talk. Thank you, everyone.
Thank you, Dr. Su. Yes, so I think due to the lack of time, we will I think skip the Q&A session, but still do feel free to just type in your questions and we will relay them to Dr. Su to answer. Yeah. So maybe Dr. Su, I just share my screen again. Is it possible? Yeah. Thank you. So right. Sorry. Yeah, so we will relay your questions accordingly or in the Zoom chat or the application to Dr. Su to answer them because due to the lack of time. Apologies for that. Yep. So just to a brief information of our next speakers. So we have our next one at 3:30 to 4 o'clock. Is a statistical analysis of the effectiveness of card counting in Indian Rami. And at 4 o'clock, we have another student speaker. Yeah, so just do check out the links later and stay tuned for for the other speakers. Yep. And I think Dr. Su, maybe you just stay on a bit longer, but the rest of the participants you may leave to the next event. Yep. Thank you so much.
Thank you.